So dear students, the topic for today will be relation between electric field and electric potential. So for that, let us consider two closely spaced equipotential surfaces. Let this is first equipotential surface and this is second equipotential surface, and let V be the potential electric potential of this first equipotential surface. That means every point on the this equipotential surface have a electric potential of V, and let V plus delta V be the electric potential of equipotential surface 2. That means every point on the equipotential surface number 2 will have a electric potential of V plus delta V. And let us indicate 2 points on each of the equipotential surfaces. This is point A and this is point P. So point P is a point of number 2 equipotential surface and point A is a point of number 1 equipotential surface. And let electric field is going in this direction, which is outward direction, and the electric field is normal to both the equipotential surfaces 1 and 2. That means electric field is outward and it is normal to both the equipotential surfaces at point A and point P in this case. And let delta L be the delta L be the distance between two equipotential surfaces. Now consider a unit positive charge, that is a 1 unit positive charge. Let us consider a unit positive charge on this equipotential surface number 2 at point P, and we are bringing this unit positive charge from point P to point A. So in doing so, we need to do work against this electric field which is going outward. So what we are going to do here is, you have a unit positive charge on this equipotential surface at very point P, and you are bringing that unit positive charge from point P to point A against the electric field, because the electric field is outward, you are bringing charge in this direction. So in doing so, you need to do some work, and work done in moving this charge will be nothing but it is charge into field will give you force, but in this case charge is unit, so only electric field magnitude is the force exerted in bringing this charge from point P to A, because charge has a unit value. So Q is basically, so Q into E is the force, but in this case your Q is unit, Q has a unit magnitude. So I am taking that in next line now. And so this is the force experienced by this charge and you are moving from P to A, and distance between P and A is delta L, basically delta L. So QE into delta L is your work done in bringing charge from point P to A. But I've told you Q here is 1 unit. That means work is E into del L. E into del L is the work done in bringing a unit positive charge from point P to A. But this work done in bringing a unit positive charge is also the electrostatic potential difference between the two equipotential surfaces. This work done will also be equals to difference in the electrostatic potential, that is V minus V plus delta V. So this will give me W is equals to V minus delta V. So V will get cancelled. So work done is minus delta V. So comparing this two, this is equation 1 and this is equation 2. So comparing 1 and 2, we have E into del L is equals to minus del V. But one thing you have to note here is, since electric field is going outward, going in outward direction, and we know along the direction of the electric field, the electrostatic potential seems to decrease. For example, if you have a positive charge here, and electric field are going all the way around for a point charge q, we know the electric field around these charges are strong. As we move away, the electric field tend to reduce by this formula. So electric field tend to reduce as we move away from the charge, because it depends upon the inverse value of the square of the distance. Similarly, the value of the potential also decrease inversely by a value of r. That means as I go away from these charges, the value of the potential also decreases. So along the direction of electric field, the value of the potential seems to decrease. Similarly, in this direction, electric field is going in this direction. That means this particular equipotential surface has lower electric potential than this particular equipotential surface, because electric field is going outward. Therefore, V plus del V is lesser than V. So V plus del V is lesser than V. So this is only possible when your delta V is negative. Therefore, your delta V is actually in negative, has a negative magnitude. Delta V has a negative magnitude. So put this delta V to be negative in this equation. So you'll get E into delta L is equals to minus will get plus, minus into minus will get plus. So E will be simply equals to delta V divided by delta L. So this is the relationship between the electric field and your electrostatic potential delta V. So your electric field is related to electrostatic potential by this relation. This is all. So electric field also can also be defined as change in the value of the electric potential divided by the change in the length. So this is it for today.